Here is a mini lesson on exponential growth and decay functions from our class notes. All right, so let's take a look at what we have here. We talked about exponential growth or decay, so we can have a function that is either growing, meaning it's also, another way to say it is increasing, or decaying, meaning it's a decreasing exponential. And the form for our exponential is f of x equals a times some b, which is a base, raised to the x power, which is a variable power. And another way to write that is we can write the b term also as 1 plus r, where r is equal to the percent increase or the rate of increase, and b is the factor or the multiplier of increase. So this is the rate or percent increase, okay? And that's always expressed as a decimal. And then the b value, we just say 1 plus r. And a is the initial or the starting value. That's the a there, initial starting value. Okay, so let's take a look at an example. We have here T of Q represents the total number of Android contracts. Okay. Total number of Android phone contracts in thousands. Okay. That's important when we interpret it. So that's in thousands that they hold at a certain Verizon store, and it's measured quarterly. Measured quarterly since January 1st, 2016. And it says interpret all the parts of the equation. So let's take a look at what we have here. So here's our standard form for an exponential. We have our initial value is our a. We have our b is our growth factor. And then we have it raised to some power. And that just usually represents time or some other variable by which it's changing. And again, another way to express b is 1 plus r. So sometimes we're given the rate of increase as opposed to the factor, multiplier factor. All right, so let's take a look at what we have given. And so we've got this expression here, t equals 86 times 1.64 raised to the second power here. And we're told that that equals this number here. Okay, let's break down what we're given here. So we know we have a as our initial value. Well, this essentially is our a. B is 1.64. And we're told that it's measured quarterly. So T represents how many quarters since January 1st. Let's put it together. So A is equal to 86. And this is contracts in thousands. B is here. Is equal to 1.64. That's our growth factor. All right, and we could find what R is. We know that B is equal to 1 plus R. So if B is equal to 1.64 is equal to, if we do a little algebra, 1 plus R, we can solve for r by subtracting 1 from both sides. We get r equals 0.64 equals 64% growth rate. All right. So I graphed it over here as well. When I put 0 into my model, I get 86. That makes sense. If I just write my general model, that is t at some number of quarters since 2016 equals 86 times 1.64 raised to the Q. Okay, this is my general form. This is my A, this is my B, and Q represents number of quarters since January 1st, 2016. If I interpret what I have here then, so this says 2 quarters after 2016, I have 305,000 contracts. That's what that says when I read that. So T of 2 equals 86.64 raised to the second is equal to 231.3056. So this says if 2 quarters have passed since January, each quarter represents 3 months. So this would say June 1st, 2016, we have, this is thousands of contracts, 231,305 contracts. Okay, we know that for every quarter after January 1st, we have a growth factor of 1.64 or growth rate of 64%. So for each quarter that goes by, we're growing contracts by 64%. All right, so here is January 2016. Here's 1 quarter goes by. Here's 2 quarters is June 2016. And then if we take 86 times 1.64, that's our growth factor, times 1.64. We get our curve over here. Let's look at another one here. So it says we have 100 milligrams of drug in our body. So that's what we're starting with. Sometimes you have to really sort of dig to say, figure out what the pieces are here. So we start with 100 milligrams and and every hour, 15% is metabolized. So we always want to figure out, is the starting amount growing or getting smaller? So if it's metabolized, we have less and less as time goes on of that drug in our body. And we're measuring that in, it says T hours since it's ingested. So T hours after it's ingested. And we want to predict how much we have after 4 hours. So whenever it says predict, it means we want to first write the general model. So here's our general form for our exponential. All right. The first piece, we usually look for is to say, what is our initial or our starting value? Well, here we start off with 100 milligrams of drug. Okay, so we start off with 100 milligrams. Okay, and then we want to find our growth factor, but sometimes we're given our rate. So here we're getting smaller at 15%. So 15%, that's our growth rate, not our factor. So our R value is negative. It's getting smaller, 0.15. B then is equal to 1 plus R. Okay, 1 plus R. So that's going to equal 1 plus, and we have a negative 0.15, meaning B is equal to 0.85, which makes sense. When B is less than 1, it means that we have a decay problem. Decay. Okay, and so let's put our general form together. We have A, we have B, all right, and we know that T is in hours. So we have F of T is equal to our initial amount, 100 milligrams, and then our B is 0.85 raised to T. And T is represented in hours. And we want to find, okay, how much is left after 4 hours. So we're just going to evaluate our function. We're going to say if 4 hours has gone by, then I can estimate how much I have left. I initially had 100 milligrams, but it's decaying, okay, at a factor of 0.85 times 0.85 raised to the 4th power. When I put that into my calculator, that gives me 52.20. And if I write that with my units, milligrams. So this says after 4 hours has gone by, I have 52.2 milligrams of the drug left in my body. And we can see here, if we graph it, it starts off here. When time is 0, I have 100 milligrams, and then it is decreasing, right? It's decaying. Decay, all right? And when I'm at 4 hours, I'm right here. So when 4 hours has gone by, I have 52.2 milligrams left.